of the router and its different interfaces provided in it for better understanding purpose. See, this would be covered in the troubleshooting classes, wherein the classes will be dealt through Cisco Packet Tracer. Physical router, I do not have a picture of a physical router at this point of time, but I don't know, I don't think so it is required for a better understanding. It's just that the router, this is the router representation. The router representation, and it has got different interfaces. We all know this blue line is an interface of the router. What is a PHP router? PHP router, that has also been answered by Mr. Pavan Kumar, and he correctly answers it that PHP is a penultimate popping router. And in order to reduce the load on the end router, PHP removes the label from the last LSR and send the IP packet to the end customer. Correct? It does, but just a small correction, it does not remove the label from the last LSR. It removes the label that is coming onto the packet from the router just before it. And it sends the IP packet not to the end customer, it sends the IP packet to the last router. The last router will send that IP packet to the customer. Okay, label stacking is the encapsulation of MPLS packet. It is different from PHP. Yes, it is different from PHP. PHP is a concept wherein you say that the second last router is doing the function of popping in order to reduce the load, like correctly pointed out by Mr. Pavan Kumar. And encapsulation is simply label stacking. That is, you can have multiple labels stacked onto one another. Next question is from Mr. Shastri. He says that how does the MPLS act in the case of route congestion at an intermediate point? Route congestion, I don't know in what context you are willing to ask that, but maybe if you are saying that if there are multiple cable cuts, and then how does the MPLS act, because now the bandwidth is limited and the paths are limited. So that actually is done based on the underlying IP protocol, the OSPF protocol, and the MPLS tables. So if there is a congestion, all the customers will get that congestion also. Or if there is a quality of service that has been enabled, and then the congestion for the priority customers will not be there. So that's a different thing. MPLS is only acting to give you the best path. MPLS is acting to give you a faster way to engineer the traffic. So that is what MPLS is doing. So I believe we will move on with the presentation. All the questions are done. We have discussed about this thing. Now let us move on to control and data plane. So this is an LSR. LSR, in a sense, we are now all very well aware what an LSR is. LSR is a label switch router, a fancy name for a router that is also doing the MPLS. So there are primarily two planes in any router. One is the control plane, another one is a data plane. What is there in a control plane? A control plane is actually having all the routing protocols. So all the routing protocols, it could be OSPF, it could be EIGRP, RIP, BGP, and whatever routing protocol is running onto that router, it will be creating its routing table. It will be creating an IP routing table, which is also called as routing information base. Now, because we are talking about an LSR and not a normal router, we are assuming that a label distribution protocol has been enabled in this router. So because LDP is also a protocol, it comes in the family of protocols, thereby it will be in the control plane of that router. From the control plane, what happens in the data plane is, data plane will have the forwarding tables. So this is very important to understand, because it also helps you to understand why the MPLS is faster, or what is the advantage of an MPLS we get by doing the switching in an MPLS scenario. So if you see the control plane, which is actually the mind of the router. We can call it as a mind of the router, because the mind will actually decide what is to be done with the routing protocols, or what is to be done and what kind of tables are to be created. This is more like a slave, you can consider, if that is the right word to say, in a sense that it will actually be pushing the packets based on that table that has been created. So it is not using any mind. So it is not using any mind in a sense that the table has been created based on the control plane, and that forwarding is happening through this data plane. So that's why these two planes are separated, so that the mindful activities, the decision maker, mindful activities happens in the control plane, the load is happening in control plane, and data plane is able to forward the packets quickly and efficiently. So because data plane has got the IP forwarding table and the label forwarding information base, the IP packets are being transferred. So to give you a more understanding onto that, see, the routing table, which is related to routing, is in the control plane. The forwarding table, which is ultimately related to the forwarding of the packets based on the labels assigned, gets created in the data plane. So from the IP routing table and the label distribution protocol, the data is actually dumped into the forwarding tables. So this is a overview of where the table actually resides and how the switching happens, how the incoming packets, which are IP packets or label packets, they move through the control plane and data plane of the label switch router, and they are able to give an outgoing IP or an outgoing label packet. So this is just an overview to differentiate between the control plane and the data plane of a label switch router. Moving forward, we will now be discussing in details about the IP MPLS tables. So from the previous session, we are aware that there are 4 kind of tables. Rather, I have spoken only about LFIB in details in yesterday, but there are tables like RIB that I have actually told you. There is a routing information base, there is a forwarding information base, and there's a label information base, that is the LIB. So these 3 tables then create the final table, which is the LFIB, which is the label forwarding information base. So based on the LFIB table, the label forwarding information base table, the packets in an MPLS network are forwarded to the next interface. So let us, in this is simple, that is, it will be created based on the, okay, let us see in the next slide, how does that happen and what kind of tables are also there in a normal route. Okay. So normal router generally will always have a routing information base and a forwarding information base. It could be a different name, but it will have a routing table and a forwarding table. So if you compare it with this slide once again, the control plane will have the routing table, the data plane will have the forwarding table. That is the concept. That is, a mind will have the routing table, the data plane will have the forwarding table, based on which the packets will just be forwarded. There is no mindful activity that is happening in the forwarding table. It has been created already. In the case of an MPLS router, that is in case of an LSR, in addition to the routing table and the forwarding table, which are actually called the routing information base and forwarding information base, there are 2 more tables, which is the label information base, which is created by the label distribution protocols. It creates the LIB. And finally, the label forwarding table, that is the LFIB, label forwarding information base. So like I was saying yesterday, that the normal router is having only 2 tables, or is having mainly the routing table. An MPLS router has got 4 tables and finally creates a forwarding table, and still it is fast because it is doing the switching based on labels. So this slide, we will actually go in details of this slide, and this will help you to understand how it works in a sense, how the tables are created, how the packets are being transferred in an MPLS network. So same, this is the location A, you can call it as Hyderabad. This is the location B, you can call it as Bangalore. So from A to B, the packet has to move. So this is A. A is the customer end router. It is connected to the first router of the Railtel service provider network. This is the interface 1. A question was being asked to show the interfaces also, but not through a physical product. I can show it through this pictorial representation. So these are the interfaces, interface 1, 2, 1, 2, 1, 2, 1. So 1, 2 is nothing but the interfaces of this router. For router 1, you have the interface 1 and interface 2. For router 2, which is actually connected to router 1, you again have interface 1 and interface 2. For router 3, you have again the two interfaces, and router 4, you have the again two interfaces. So what is important to note here is that interface number 1 is connected to A, which is the customer location. Interface number 2 is connected to B, which is the customer location. The packet is flowing in this direction. See, this is being shown here. The packet flows from A to B. A is in Hyderabad, B is in Bangalore. There is a network that has been provided by Railtel. So it actually goes through these series of routers. So for simplicity, only 4 routers have been shown. Now let us also label our understanding. We already know that this is the CE router, right? This is the customer edge router. This is the customer edge 1. This is customer edge 2. This is the provider edge 1. This is the provider edge 2. This is the provider router. This is the provider router. Who will be the PHP router in this scenario when the data is flowing from A to B and there are only 4 routers in the example? This will be the PHP router. Why this will be the PHP router? Because he is LER minus 1. He is egress minus 1. So this is the egress router and this is the ingress router. Okay. I believe your understanding of the concepts or the terminologies that we have discussed so far will be clear from this particular slide, wherein we define the customer edge routers, the provider edge routers, the provider routers, the PHP routers, and we will also be able to correlate it to the fact that who is doing the pushing, who is doing the popping, who is doing the swapping. We will again understand further. And we can also now understand the LSP. We will try to see how the LSP gets created. What will be the LSP or the label switch path when the packet is flowing from A to B. Okay, so what happens here is, please note the color coding also, because that will help you to correlate what gets created in what table. So first of all, the RIB, which is in the black color, which is the routing information base. What happens is that this router, now how is this being represented? This particular thing is for this router. Okay. This particular thing is for router number 2, and then router number 3, and then router number 4. Okay. So whatever is being written below that router is actually what is happening in the control and data plane of that particular router, is actually the content of the tables, the RIB, FIB, LIB, LFIB tables that are being created in that router for the data packet that has been destined to go to destination B. Okay, so let me erase everything and again start in the sense this has given you a basic understanding of what this picture is. The terminologies of MPLS have been also told in the slide. So what we have is we get a packet on the interface 1 of router 1 with the address as B. What is B? B is the IP address of B. Okay. So what information does router 1 gets? Router 1 gets that he has to forward the packet with an IP address which is of B location to router number 2. Okay. That is the only information till now. The moment you have enabled the routing protocols on this router, this router will actually try to find out a path for the destination B. What is B? B is actually the IP. So it can be 192.168.1.2. So this 1.2 is actually B. A location which could be 1.1, that is 192.168.1.1, wants to communicate with 1.2. So wants to communicate with 1.2, that means he is having an IP packet which is having a destination address of 192.168.1.2 and a source IP address of 192.168.1.1, and it sends to the router 1 on the interface 1, because interface 1 is connected to the device A, to the router A. Router 1, which is already having an interior routing protocol such as OSPF running in its domain, finds out how it can go to the destination B. Till now the MPLS has not been enabled. Okay, so it is all black. Black means it is RIB. It will always happen in the case of a normal router also. So it says that I can transfer the packet to the router number 2. That's all it knows. Okay, we are going step by step. We are going step by step in order to understand what actually happens inside a router when a packet with a destination of 192.168.1.2 comes from a source of 192.168.1.1. The router 1 only gets to know that it has to give it to router number 2. How it has to give? No idea. Fine. So what entry gets into router 1? RIB, black color, is that B corresponds to router 2. Okay. After that, it creates a forwarding information base. That is this red color, or red color or the pink color. This is the forwarding information base. That means in order to reach to router number 2, that is this router, the router 1 should transfer the packet to the interface number 2. That's logical, right? The logical is, if you want to reach this destination number B, you have to give the packet to router number 2, because you are not directly connected to the router number B. You will have to give the packet to router number 2 through the exit interface number 2. So that information is being calculated based on the forwarding information base. The forwarding information base will find out what is the interface that is connected to router number 2. So this information gets populated. So this is a normal router. Okay, even if you forget that there is no MPLS running, so what you have right now so far are these things. You have got these tables will get formed in all of the routers. Okay. These two tables, that is the RIB and the FIB. We have already discussed that in a normal router, the RIB gets formed, the FIB gets formed. It moves on to the router number 2. We are going step by step in a sense that packet came from 1.1 with a destination of 1.2. So that will be entered in the routing information base of router number 1 as B: router 2. Okay. And it will create a forwarding information base saying that in order to reach router number 2, you please move the packet on the exit interface number 2. Fine. The router number 2 receives the packet on the incoming interface number 1, and it says that, oh, I am not directly connected to B. B, which is 192.168.1.T2, is not my next neighbor. It is not my peer. So I cannot reach directly to him. I have to find out who is the next peer. So he sees that router number 3 is the next peer node which is connected to router B somehow. He only has a visibility of router 1 and router 3. Okay. So he gets an entry of B: router 3. That means in order to reach B, he must transfer the packet to router number 3. How should he transfer the packet to router number 3? On the exit interface 2. So that information gets populated here. That is BR3 now becomes BR32. Okay, so please try to relate it to the control plane and data plane as well. Control plane is the mind which actually finds out that B is not my direct connection. It has to go through R3. This has all been found out by the control plane. And he says that please give it on the exit interface number 2. So the data gets dumped onto the forwarding information base, which says that the exit interface's router is interface number 2. Okay, I hope all of this is making sense because it's only a starting and we will be going into depth now. Same thing happens for router number 3. He gets BR4. Why he gets a BR4? Because he again sees that the destination is B, which is 192.168.1.2, and he is not directly connected to me. I have to give it to router number 4. How he gives to router number 4? Through the exit interface number 2. Okay, so this gets populated. Now it comes to router number 4. He sees that B is indeed directly connected to me. So this is a direct connection. So he says that B is a direct connection. And how does it give it to B? It is directly connected on the interface number 2. Okay. So this is all that is happening in a normal router. A normal router is doing an IP lookup. Very important to note that it is always an IP lookup. Why it is an IP lookup? Because he has to look up onto the destination IP and every time find out what is the next connected router or whether that IP of the destination is directly connected to him and decide on the exit interface. This is a lot of work for the router. This is not a small job for the router. The router has to every time find out the destination IP address by giving a lookup onto the IP, consulting its control plane, and then finally forwarding to the forwarding table created in the data plane. How does MPLS pitch in? MPLS pitch in through the color green. Okay, so let me again erase all these things. We got to know the normal behavior in a normal router which is not running an MPLS. Okay, now the same router we all know can run MPLS, so we enable the LDP or the TDP. Okay, this is the label distribution protocol or the tag distribution protocol. Again, we discussed yesterday, TDP is Cisco proprietary. When it was introduced, it was not free, and LDP is the free protocol, just like OSPF, that is a label distribution protocol. So the moment you enable LDP or TDP, the LIB starts to get created. The LIB starts to get created means the label starts to get created. Label start to get created implies that a random number from that 2 to the power 20 labels, which are again reusable, is given randomly. Now, how is it given randomly is like this. It says that the location, the B. So please concentrate on the green colors because the green color is the LDP TDP that leads to the formation of the label information base. What happens in the LIB or the control plane? I hope you understand that this goes into the control plane. It is not in the data plane. Just like the RIB, the routing information base in the control plane, the decision or the mindful activities are being done in the control plane of the router. In a normal router, the label information base is also done in the control plane of the router. He says that the destination B is actually equal to 101. 101 is a label that is just assigned locally. So this is a local label that has been assigned to number B. Number B in the sense, now 192.168.1.2 is no longer 192.168.1.2. It is actually the label 101. The moment you assign a label 101, your job is made easy. Why? Because you no longer have to do an IP lookup. You no longer have to look onto the destination IP. You just have to see the label, and based on that label, you will be moving forward. Okay. What it also does is all of them will be having a local label. So this first line, you concentrate on this first line, that is BLOC 101, BLOC 201, 301, and so on. They will all generate the local label for the destination B. Okay, so the destination B, which is 192 192.168.1.2 will have a local label of 201, 301 and so on. For simplicity purpose, router 1 will generate the local label 101, router 2 201, router 3 30. Otherwise, these are all random numbers. The router number 4, which is actually directly connected to the destination, will have a local label LOC of number 3. What is number 3? Number 3 is implicit null. What is implicit null? It is one of the reserved label in the 2 to the power 20 labels of the MPLS labels. So we discussed yesterday also that nearly 15 labels are reserved in the MPLS label. One of them is implicit null. Implicit null means a value of number 3 means I am directly connected to the destination B. So this is also important. Why? Because the egress router will always have a label, a fixed label number. It is no longer a random number for the directly connected destination. That will be number 3. Okay. After this, what happens is that they keep sharing. They start to share their information. They start to share their information implies we have yesterday discussed about various messages in an LDP protocol. Just like an OSPF protocol has got hello messages and then exchange messages and keep alive messages or notification messages, the LDP also has got the exchange messages. So they start exchanging their information. Why? Because it is always good to exchange the information with your neighbors. That's what we are doing in this class also. I am trying to share the knowledge I have with you. So these routers also try to share the knowledge they have. What knowledge they have? They have the knowledge that destination B is 101, destination B is 201, 301 and it is implicit null for them. Okay. So router 2 tells to router 1 that I have the information that B is 201 for me. So router 1 notes down in his LIB, in his label information base, that B is equal to R2 is equal to 201. Why do so? Because he is not directly connected to B. He has to actually give the data to B. How it will give data to B? He gets to know from his neighbor, the directly connected peer from router number 2, that B is actually 201. B is 101 for me for router number 1, but it is actually 201 for router number 2. So he stores that information. It's an important information because he gets to know that B can be reached through router number 2 with the help of 201. The router number 2 gets the information from his neighbors, that is B is actually 101. So he stores B is router 1, 101. He gets the information from router number 3 that B is actually router number 3, that is 301. Okay. If it is becoming a lot of information, what I would like to tell you is that simple logical or simple common sense, even for human beings, would be you want to reach, for example, this Bangalore. Okay. You are actually starting from, let us consider A to B, Ahmedabad, for easy understanding. So you take a car and you start from Ahmedabad and you want to go to Bangalore. Okay. From moving from Ahmedabad to Bangalore, number of cities will come into picture and you do not know where exactly the Bangalore is. So you start from Ahmedabad, you go to the next city. You know the way, you know the direction, you know the path to reach the next city in the path to Bangalore. So you goes to the next city, that is would be the city at place 1. So whatever city that comes into picture. In that city, you meet some people and they tell you, okay, you take this particular road to reach router number 2. Okay, there is no Google map till now. We don't have Google map. We are living in old worlds and we have to move from Ahmedabad to Bangalore and we just know the direction or the path to reach the next city. So you reach to the next city, city number 1. City number 1 tells you the path to reach city number 2. But city number 2 also does not know the direct path to Bangalore. It tells you to reach city number 3. City number 3 tells you to go to city number 4. City number 4 tells you that, oh, Bangalore is directly connected. You can go Bangalore immediately. So what my point is, just like a common logical thing will happen if someone wants to move from Ahmedabad to Bangalore, but does not know where exactly the Bangalore is, and will have to depend upon the intermediate cities. Same way, the routers which are actually not connected to the destination address will have to take the help of the intermediate routers, because the intermediate routers knows the next path. They knows the path to the next router. That's what is happening in this label information base. That's what happened without an MPLS also, because without an MPLS, the router B, if you concentrate on the red table, got to know that B is connected to router number 2 on exit interface 2. Then router number 2 got to know that he is not a direct neighbor for me. It is connected to router number 3 on exit interface number 2. Router number 3 got to know that he is connected on router number 4 on the exit interface number 2. Fine. Same way happens in the LDP protocol also, and an LIB gets created. So let me go to the final thing onto this. That is, an LIB gets created. I hope it is clear. The LIB gets created, and what is the final entry in the LIB? These are the final entries. Okay, these are the final entries. These are the final entries. These are the final entries. Router number 3 gets to know that the destination number B is actually a direct neighbor of router number 4. Why? Because he has an implicit null. He has implicit null. He has a label 3 onto it. Okay. Fine. So this is also deciding who will be the PHP. How it will decide who will be the PHP? Based on this label number. We got to know earlier that implicit null made this as an egress router because he was a direct connection. When he shares this information with his neighbor, that is router number 3 gets to know that router number 4 is a implicit label. Okay, so router number 3 will actually become a penultimate hop popper for this connectivity. Finally, what you get is a label forwarding information base, which is the blue color, which is nothing but it will pick the final values. It will try to, I would say, optimize the label information base. Optimize the label information base by saying that earlier he has given a local label to local label of 101 to destination B. He got to know from his neighbor that B is also equal to R2 is equal to 201. So he writes that information. B is R2 is equals to 2 is equals to 201. Why R2 is equals to 2? It is here. Correct. Now everything is getting combined. Everything is getting combined means all these three tables, which are the RIB, which is the FIB, and which is the LIB, all these will be compared, and a final entry, this is the final entry, will be entered in the LFIB table, and the most optimized way. Okay, so you can compare. So B is R2, we know. R2 is 2, we know from the FIB. 2 is 201. Why? Because R2 is equals to 2. So it is all, what it is doing is it is equating. It is equating that B is R2, B is also 2, B is also 201. Fine. And the second entry is that B is also 101. That means my local label for the destination B is 101. So if I get a packet, which is either a label number 101, I will give it to R2 with an exit interface of 2, and I will swap the label with 201. That is what the information is. Okay. Or if I get a packet which has a destination IP address of 192.168.1.2, I will give it to the router number 2 on the exit interface 2, and I will assign the label 201. That means I will push the label 201 onto it. And this is called a forward equivalence class. Why it is called a forward equivalence class? Because it can be either an IP packet, that means the destination B, that means 192.168.1.2, or it can be the label 101. I will treat it in the same way. What will be my treatment? My treatment will be R2 to 201. This will be my treatment. Whether I get B or I get 101, I will treat it this way. Same way the table is created for router number 2 and then for router number 4, but router number 3, But the router number 3 knows that the router number 4 is the egress router. Why it knows that it is the egress router? Because the label value is number 3. So he will actually do the operation of pop. So he will actually become the PHP and he will pop out that label and give the plain IP packet to the router number 4, which will actually transfer it to the destination B. Okay, so this is the thing that is happening inside a LSR, inside a label switch router, in terms of the tables that have been created, in terms of how the MPLS moves from one destination to other destination using the tables. Why it is faster? It is faster because the requirement for IP lookup at these intermediate routers is not needed now. Earlier, if you will compare, the router number 2 and router number 3 were always doing the IP lookup. But now if you see, there is no IP lookup involved. It is only the swapping, pushing or popping of the labels. Only the last routers in that series will be doing the IP lookup. Now this may sound very simple because it has 4 routers, but when those routers become 40, this becomes very important and it saves a lot of time, because in the chain of 40 routers, only the first and the 40th router will be doing the IP lookup. All the other 38 routers will be enjoying and doing the swapping operation, which is not opening the IP packet and simply swapping it with the next label based on this info. Okay, with this, I will take the break in the sense we will go for a break and I will like to address your queries because it's just 10 minutes to 11. Let us have your queries because otherwise all this will be lost. I'm pretty sure. If you have any queries, please go.
Ankur, can you hear me?
Yes, I can.
What I have understood from this is, now between Ahmedabad to Bangalore, if you have 4 routers, 1, 2, 3, 4, what label router number 2 has to be used is decided at the router 1 itself. So router 2 has to use the label 201. It is already decided at router 1. Similarly, router 3 is basically knows the next router is there, so it will decide to pop. So that is in advance, it is being created. There is no need of looking up.
I would like to start by saying that the label 201 was not decided by router number 1. It was decided by router number 2. If you see this thing.
Okay.
So why it is 201? Just for the simplicity, router 2 means 201. So 201 will be created locally by router number 2. And that information will be exchanged with router number 1 and router number 3.
But how that information is helpful to router number 1?
Router number 1, it is helpful because till that information is not shared, router number 1 knows that it's equal to 101. But he does not know where do I have to forward this. B is not directly connected to router number 1 and he doesn't know what B is connected to. But when router number 2 gives him, he gets a hope. Okay, maybe I can give it to router 2 and my job will be over. Router 2 will look out where he has to give it. So that information to reach the next city, I would say, in the path.
So that means sending information about 201 to router 1 is a confirmation that I have a connection to it and I will forward this by that port to 2.
Yeah,
by router 2.
That is a confirmation that I know something about the destination B, but that something is not complete because B is not directly connected to me. Only router number 4 is the final authority in this because B is directly connected to me. So that's why he gives a label of 3. So all these routers 1, 2, 3, till they not get the number 3 as the label from their next neighbor, they all assume that the next router will give it to some other person.
So it means the next router, until it forwards the label number, this packet will not be forwarded from forward direction.
Exactly, exactly. And that is all to understand who has got number 3 label. Number 3 label is never assigned until and unless that router is directly connected to the destination. So that is a reserved label. They are all in circle. If they don't get number 3, they assume that the next person will do the job. Next person means next router will do the job.
For example, in this particular diagram, for Bangalore, fourth is the implicit null. Similarly, in between, some stations will be there for which router number 3 can be implicit null.
Yes, it can be. If there is a direct connectivity, for example, there is a city C, Chennai, that is a location Chennai. In that case, this will now have C comma R2. Okay.
Yeah.
So this will actually have C is directly connected. And then C will be assigned a implicit null label of 3.
So this all will be.
Please.
This all will be taken care by LIB.
All this will be taken care by this protocol LDP. The moment you enable the LDP protocol, the LIB gets created, and that LIB in turn creates LFIB by taking the information from all 3 previous tables.
Okay. So it is not simply as it seems actually.
Exactly. That's what I wanted to tell you, that how complex it is for a router to do the job. We are happy people who don't have to do anything. And that's the reason why MPLS is so widely used. See, even if I am an MPLS engineer who does not know how these things are treated, I can just write a command saying that NDP is enabled and my job is done. Had it been 80, I have to actually define these tables. I have to manually do it and have special knowledge onto it. So that is the reason why MPLS is there for 30 years. The way we discussed yesterday.
True, correct. Okay, thank you, Ankur. Anybody else, please ask questions.
Yes. These labels are not fixed. They are randomly changing, and they are more addition to it, which is VRF. See, this 192.168 1.1 and 1.2 will be used by multiple customers. Like I have told yesterday, 192.168 1.1 can be used by Indian Railways and by DRDO also. Had these labels been fixed, it would create a problem. So they are actually created randomly based on that connectivity, and then with the help of the VRF, RD, RT, which we'll be discussing going forward, they get. So even label assigning, which is random, is a complex behavior inside. Yes, they are. For every destination, there is an entry. There is an F entry, there is an LFIB entry. Why it is still faster? Even in a normal router, RIB, FIB is there for every packet, right? For every destination, there is an RIB and an FIB. But because an IP loop is not happening, this entire job becomes fast.
Yeah.
Exactly. So that was a fixed thing, which we yes, exactly. So we had to define it fixed, and we have to manually fix it. Yes. Exactly. So that's what the protocol is doing. That's what the protocol LDP is doing. That fastness, which was early manual, is now being taken care automatically, and the traffic engineering, which was to be manually defined in ATM, is being done with the help of these tables. Now, how that is, the simple answer is this protocol is doing that. Now you can also say why then OSPF is there. See, OSPF is also doing the same job, right? And
So that means that.
So simple answer is a protocol. Protocol is the answer to all the automation.
Mohan Krishna,
From the same source and same destination, the subsequent packets will take another table or same?
No. They will take the same. Once
Same
the path
level.
has been established,
Okay.
they will all be now fixed in that VRF with the same path.
So that should have some lead time. No? Means to which time they will wait for any delay for packets. Means if there is no packet for some fixed time to the same source to same destination, how much time that table will be in the base?
That simply will depend upon the messages of the LDP, the way we have keep alive messages in OSPF, the hello packets in OSPF. Same way, like we discussed yesterday, there are session messages and the notification messages, they will decide. So after every third notification message, if the router is not live, that destination is not live, it will be erased. So that is happening continuously and automatically.
Narasimha,
Sir.
See again, that will decide it. For example, if there are two paths, there is one more path out here. Okay, that is by router number 5, 6, 7, which obviously will be. So the OSPF protocol will come into picture if in case the OSPF is used, because we know that MPLS is dependent upon OSPF or the interior protocol that is running. So this routing information base, here itself that decision will happen. Whether the B will go to R2 or whether the B will go to R5, here the cost will be written. Whether this is a 1G link or this is a 500 Mbps link, that information will be done here only. That is exactly. But then in case of MPLS, you can use it with the help of LDP protocols. You can manually intervene and then use it. That's what it is. So you can, another protocol is there, which is a resource reservation protocol. In the resource reservation protocol, which we will not cover actually, the RSVP protocol, the path is actually fixed before. So there you can define that 500 Mbps path has to be used. Or when there is a label stacking, then in case of congestion, you can define based on those label stacking that 500 Mbps path has to be used. So that is again advancements that happens based on the path if you want to use it always. LDP can also be used, RSVP can also be used. Okay, I'll just look on to the chat window. I believe there are questions. Could you repeat how 101, 201, 301 labels are created? 101, 201, 301 are created the moment you enable the LDP protocol. Okay, so this LDP protocol, the green color, this green color, this green color is done the moment you enable the LDP protocol on those interfaces. It is all automatic and it is all random. If cable cut occurs between router 2 to router 3, then what happens? If a cable cut occurs between router 2 to router 3, then whatever new path is there, if the router 2 is connected to other routers also, now this is the case. Then this information, that is, this is number 4, 5, 6 or whatever that number is, his tables will get populated again based on those session messages and notification messages. He will get to know that router 3, the path to router 3 is no longer available. I must reroute the packet through a new path. Okay, the next question is, it goes through other route. What happens with label? The label gets changed. The label will be randomly assigned by the LDP protocol. What are the implicit labels and how many reserved for? Implicit label means number 3. Implicit label simply means the value will be number 3. It implies that I am directly connected to the destination. I, in the sense, the router is directly connected to the destination. There are 15 labels that are reserved for different functions. Is any lease time for MPLS label like DHCP IP? Okay, there is nothing like that. It is very fast. There is no lease time as such, and there are two different things. Okay, with this, the questions are also over. I believe we can go for a break. If in case there are more questions, let us have it on the chat window. I'll take it.
Okay, Ankur, we'll stop here. We'll come back again at 11:15.